Hi everyone. So in this video we are going to start studying about light propagation in optical fiber. A very simple topic, a very straightforward topic, and these kind of topics we have already studied in our higher secondary classes. But we will start right from the basics. It is mentioned in our syllabus. That's why we need to cover it. Okay. So what is happening here? There is a boundary which is differentiating two mediums. This is your medium 1. This is your medium 2, and this is the boundary. Below this there is medium 1. Upper this there is a medium 2. Medium 1 is there, this is the medium 2, and this is your boundary, which is a plane. Now what is the perpendicular of this plane? This line. Perpendicular of this plane is this line, and that is known as normal. I will call it normal. I will call this line as a normal. So now this is the plane and this is the normal from the plane. Now what will happen? The wave will come. The wave will come and strike the boundary plane like this. Wave is coming and striking the boundary plane like this. Now what will happen? Some part will be reflected back and some part will be transmitted. So as of now, I will care about the transmitted part. Some part will be reflected back and some part will be transmitted. So now we are caring about the transmitted part. So this is our transmitted part. Now this transmitted part will make some angle with the normal. It will make an angle theta r with the normal. Now this theta r could be greater than theta I, or it could be lesser than theta I as well. This theta r could be greater than theta I as well. It could be lesser than theta I as well. What I mean to say is that this is your normal. This is your normal, and wave is striking like this. Now some part will be reflected back. It will be reflected back like this. So it would be near to the normal, or it could be far away from the normal. What I mean to say is that the reflected line can be here as well. It can be here as well. It could be here as well. It could be here as well. It could be here as well. So where it would be, that depends on the epsilon r values. Okay. So here they are asking us to find this transmission angle. Sorry, this is theta t. This is your transmission angle. This transmission angle we need to find. And for that, which law we use? If you have studied EM wave, when you are studying about oblique incidence, there I told you one law. What is that? Snell's law, right? Snell's law. So in Snell's law, I taught you beta 1 sin theta I is equals to beta 2 sin theta t. Or what I can write down? Epsilon r1 sin theta I is equals to epsilon r2 sin theta t. Or what did I teach you? We can write it in terms of refractive index as well. This is not intrinsic impedance. This is refractive index. So n1 sin theta I is equals to n2 sin theta t. So what is n here? N is not intrinsic impedance. This is refractive index. Refractive index. N1 is the refractive index of medium 1, N2 is the refractive index of medium 2. So let's start solving the problem. Yeah, so in the first case, under root epsilon r1 sin theta I is equals to under root epsilon r2 sin theta t. So this is what I need to apply. So under root epsilon r1 sin theta I. Sin theta I is 45 degree. Theta I is 45 degree. This is given. The incident angle is 45 degree. What is epsilon r2? That is under root 2 into sin theta t. Right? This is Snell's law that we already know. So sin 45 degree is 1 by under root 2, and this under root 2 will come here. So sin theta t is coming out to be 1 by 2. And what is theta t? So that would be 30 degree. So transmission angle is 30 degree. Now if I make the diagram for this case, then this is the boundary. This is the boundary. And this is the normal to the boundary. My incident wave was making normal to the boundary. This is the normal to the boundary. My incident wave was making an angle of 45 degree with the normal, but a reflected wave is making an angle of 30 degree with the normal. That means it is moving towards the normal, right? It is moving towards the normal, because this is 30 degree, this would have been 90 degree, this would have been 45 degree. This is 30, this is something else. If you are in the same line, that means this would have been 45 degree. And this would have been some 50 degree or 60 degree, anything. But this is your 30 degree. That means it is moving towards the normal. So this angle is 30 degree. And here my epsilon r1 was 1, epsilon r2 was 2. So here epsilon r2 was greater than epsilon r1. Are you getting this point or not? So it is moving towards the normal. So this is how my wave was going, but now it has moved towards the normal, right? Now for the second case, the same thing I'm going to do. Here epsilon r1 is 4 and epsilon r2 is 3. So under root 4 sin 45 degree is equals to under root 3 sin theta t, right? All good? Okay. So 2 and this is 1 by under root 2. So this is 2 and this is 1 by under root 2 and this is 1 by under root 3 is equals to sine theta t. So sine theta t is under root sine theta t is under root 2 by 3. So for this I need to use the calculator. Two by 3 under root sine inverse. So this is coming out to be 54.73 degree. So what did you understand here? Here if I make the diagram, if I make this particular diagram here, that with the vertical line, with the normal, I am making an incident wave is making an angle of 45 degree. Incident wave is making an angle of 45 degree with the normal, but the reflected wave is moving away. Reflected wave is moving away because it is greater than 45 degree angle. So reflected wave is moving away. This angle is 54.73 degree. With here what was the case? Epsilon R1 was 4 and epsilon R2 was 3. So here your epsilon R1 was greater than epsilon R2. Now what does epsilon value tells? What is the value of epsilon R for air? What is the value of epsilon R for air? That is 1. And for water it is, as far as I remember, for water it is 3 by 2. I don't remember it exactly. But I guess for water, epsilon R2 value is 3 by 2. Now which medium is denser, water or air? In air you can move your hand very easily. But in water you have to put more force to move your hand. Right? In air, if I ask you to move the hand, very easily I am moving it. But in water I will have to put more force. So that means more epsilon value means more denser medium. Denser and rarer, there are two terms. Rarer medium means where particles are very far away, so you can move your hand very easily. In denser medium you need to move your hand with good amount of force, right? So there are two medium, rarer and denser. Here which medium is rarer? This medium is rarer and this medium is denser. Here which medium is rarer? This medium is rarer and this medium is denser. So more epsilon R value means more denser medium. So when you are moving from denser to rarer medium, your wave is moving away from the normal. And when you are moving from rarer to denser medium, your wave is moving towards the normal. Are you getting this point or not? This is the first point. The second point, if I increase this value, if I increase this theta I, if I increase this theta I, that means let's just say I make it 60 degree. If I make this 60 degree, then what will happen? This will move towards this direction. Are you getting this point? If my incident angle, let's just say here my incident angles become 60 degree. So what I will write down here? Under root 1 sine 60. What is sine 60? Under root 3 by 2 into under root 2 sine theta t. Right? So what will be my theta t? Under root 3 by 2. Okay, this is not possible actually. This is not possible. This is actually not possible. We will talk about this scenario later on. But let's not take this example. What I really mean to say is that if we talk here, here what I was saying, that my incident angle is 60 degree now. So what is the value of sine 60? That is under root 3 by 2. And here what I am gonna write? Under root 2 and sine theta t. Yeah, this is possible only. Sorry. So what will be theta t here? So under root 3 by 2 root 2 and then sine inverse. So what you are getting? And then take the sine inverse. So you are getting that angle to be 37 degree. So your theta t increased. That means this angle increased. Basically, this is very, like, intuitively also you can understand. Like, this is how the wave is going. Initially the wave was making an angle of 45 degree with the normal. Now if you move the wave like this, then this reflected wave will also move. If this wave goes here, then the reflected wave will go here. So if you increase the incident angle, then reflected angle will also, the transmitted angle will also increase. If you increase the incident angle, then transmitted angle will also increase. That is the one thing. And now the second point is, if you move from denser to rarer medium, then your wave moves away from the normal. If you move from denser to rarer medium, then your wave moves away from the normal. And if you move from rarer to denser medium, then your wave moves towards the normal. Say yes or no. All good? So these are the points. Based on this only we will proceed in our chapter. So this is what I have written. Higher epsilon r means denser medium, lower epsilon r means rarer medium. And yeah, this is the thing, like refractive index. What is refractive index? This is your refractive index. So that is proportional to your epsilon r. Say yes or no. What about beta? Beta is also proportional to epsilon r. And what about What about intrinsic impedance? Intrinsic impedance is inversely proportional to epsilon r. If you remember it clearly, I hope you remember it. What is intrinsic impedance? That is 120 pi under root mu r by epsilon r. So it is inversely proportional. What is beta? Beta is omega and under root mu r epsilon r, omega by c under root mu r epsilon r. So beta is proportional to under root epsilon r. And same goes for refractive index. Refractive index is also proportional to under root epsilon r. Because what is refractive index? Refractive index is c by vp. And what is vp? Vp is c into under root epsilon r. So n is equals to under root epsilon r only. Okay, so n is equals to under root epsilon r only, considering that mu r is equals to 1. Then this formula is applicable. And in 99% of the cases, mu r will be 1 only. But you just need to remember the proportionality. You just need to remember the proportionality, that beta is proportional to under root of epsilon r. Refractive index is proportional to epsilon r, and this intrinsic impedance is inversely proportional to under root epsilon r. Okay, and when waves move from rarer to denser medium, it moves towards the normal, and when wave moves from denser to rarer medium, it moves away from the normal. This phenomena we have seen here. Now, what is my target? What is my requirement? My requirement is, what I will do is that I will keep on increasing the value of theta I. If I keep on increasing the value of theta I, what will happen? The theta r value will also increase. And now from where to where I am going? I am going from denser to rarer. That means it is already away from the normal. This angle theta r is already away from the normal. So what I will do is that I will keep on increasing the value of theta I. And at that point I will stop when theta r becomes 90 degree. That means my transmitted wave is normal. My transmitted wave is parallel to the boundary surface. Where I will stop? I will keep on increasing the value of theta I, and I will stop at that time where my theta r becomes 90 degree. That means my transmitted wave becomes normal to the boundary surface. This is my target. Okay. So if we keep on increasing the value of theta I, then theta r increases. At some value of theta I, what will happen? Theta r becomes 90 degree. Why do I want to achieve that? Now let's just say at some value of theta I, theta r becomes 90 degree. So that value of theta I am calling as theta c. So when your theta I is equals to theta c, at that time, here I am writing, when your theta I is equals to theta c, at that time your theta r is 90 degree. Let's just say this theta I is 60 degree. I am assuming a random value. Let's just say this theta I is 60 degree. Now if I apply theta I to be 61 degree, if I apply theta I to be 61 degree, then what will happen? This theta r is already 90 degree. If I increase it more, then theta r will increase more. Now if theta r increases more, let's just say theta r was already 90 degree, and let's just say theta r becomes 91 degree now. So what will happen? What will happen? This is the boundary plane. This was the angle. This angle is 60 degree. Now I increased it to 61 degree. At theta I equals to 60 degree, my theta r was 90 degree. Now I have increased this angle to 61 degree. So now my theta r will increase greater than 90 degree. That means it has to be 91 degree. And where will be 91 degree? This would be somewhat around 91 degree. That means your incident wave is coming back into the same medium. Your incident wave is coming back into the same medium. And if it is coming back into the same medium, that means it has to follow the law that your theta I should be equals to theta r. What I mean to say is that I sent this wave and it was somewhere here. Then I keep on increasing the value, it came here. Then I keep on increasing the theta I value, it came here. And when I increased it further, what happened is that this wave has to come here. And when it came back to the medium, then there is a rule that whatever the theta is there, the same angle has to be there as well. Like this can never happen. That you are saying that sir, this angle is 61 degree and the wave is reflected back like this, and this angle is somewhat around 89 degree. This can never happen. This is wrong. This can never happen. Just as the wave comes back into the medium, it will be reflected back with the same angle. So I kept on increasing the value of theta I. At some angle of theta I achieved theta r to be 90 degree. And when I increased theta I value more, what happened was the wave was coming back into the same medium. And if the wave is coming back into the same medium, it has to be reflected back with the same angle. Now what I did is that this is how I am sending the wave, and there is no reflected wave. The wave is coming back. Okay. And this phenomena is known as total internal reflection. Now again, I am saying a very important point. For this lecture, I am saying that for theta I greater than theta c, there will be no wave in the medium 2. But in the next lecture, I will teach you that certainly there is a wave in medium 2. Okay, but in the next lecture. For this lecture, what you need to study, that this is my incident wave, and if I increase theta I greater than theta c, that means if I increase my theta I greater than 60 degree, then what will happen? My theta r should be 91 degree. But that 91 degree cannot happen. That means it has to be reflected back with the same angle. So that means here there is no wave. As of now, you need to consider this thing, because this is what we are studying, that we have studied in higher secondary classes. This is something that you study in 12th class. But in engineering, you will study something else. But that I will tell you in the next lecture. Certainly here there is a wave. Okay, this wave will be traveling in a certain direction with the decaying amplitude. So that concept we are going to see in the next lecture. A very, very interesting concept and a very, very important concept as well. But in the next lecture, for optical fiber, what you need to understand, that my wave came for a greater angle than theta c, it will be reflected back. That's it. All good? Let's do the analysis with some equations. So I hope you must have got my point. Now, to achieve this phenomena, I need to use denser to rarer. I cannot use this phenomena. What I mean to say is that, let's just say this is my incident wave, right? This is my incident wave. This is my rarer medium, and this is my denser medium. To get this phenomena, to get all these things, I have to go from denser to rarer only. If I go from rarer to denser, then what will happen? Assuming that this angle is 45 degree. Now where will be the transmitted wave? The transmitted wave will make a smaller angle with the normal, because this is a denser medium. So let's just say it is making 30 degree angle. We are using this scenario only, 45 degree and 30 degree. This was rarer, this is denser. Now what will happen? I will keep on increasing the value of theta I. Then this theta r will increase. Certainly it will increase. I will keep on increasing. Even if I make this 90 degree, even if I make this angle 90 degree, still your theta r will not be 90 degree. Why is that so? Here at 60 degree, my theta r became 90 degree. But here, even if you make this incident angle to be 90 degree, your theta r will never be 90 degree. Why is that so? Because if you keep on increasing, this is increasing, but this will also increase here. But till what point it will increase? Already there is a difference of 15 degree, no? This was 45 degree, this is 13 degree. So this is already behind. This is already close to the normal. You need to make it away from the normal. So when you go from denser to rarer, then this phenomena can be achieved. But when I go from rarer to denser, this phenomena cannot be achieved. You can check with this example as well. Let's just say I made theta I to be 90 degree. So what is sine 90? That is 1. What is this medium? Having under root 2 sine theta t. So what is sine 90? 1 by 1, and this under root 2 will come here, sine theta t. That means your theta t is becoming 45 degree only. So even if I had sent the wave like this, then my reflected wave will be like this only, 45 degree. So this is the maximum angle I can achieve. In this scenario, this is the maximum angle I can achieve, that my theta t is 45 degree only. But what do I require? I require my theta to be 90 degree. What do I require? I want my theta, not r, this is theta t, sorry. This is theta t. I want my theta t to be 90 degree. Why do I want it to be 90 degree? Because after that 91 degree I cannot achieve. If I go for 91 degree, that means this will be reflected back here. So this will be equal to this one. So let's see the mathematical scenario of all these things. Now we are going to see the mathematics. Okay. So first thing is that we need to go from denser to rarer. And secondly, at theta I equals to theta c, we will get theta t equals to 90 degree. And this is known as critical angle. What this is known as? This is known as critical angle. Okay. So the value of theta I at which theta r is 90 degree is known as critical angle. The value of theta I is achievable only when the wave travels from denser to rarer medium. Is that okay for you? Now let's find the value of theta I at which your theta r becomes, at which your theta r, I should not say theta r, I should say theta t, at which your theta t becomes 90 degree. So we need to find the value of theta I. Okay. So what we are going to apply? We are going to apply Snell's law only. So under root epsilon r1 sine theta I is equals to under root epsilon r2 sine theta t. And what is sine theta t? 90 degree. Okay. So what you are getting? Sine theta I. This is 1. This is also 1. Sine 90 is also 1. So sine theta I is equals to. So at theta I is equals to theta c. At theta I is equals to theta c. This scenario will be achieved. So instead of theta I should write theta c. Because at theta I is equals to theta c, your theta t would be, when your theta I is equals to theta c, at that time your transmitted angle will be 90 degree. So this is theta c, this is theta c. So sine 90 is 1, right? So what is sine theta c here? 2 under root sine inverse. This is not achievable. Sorry. From where to where we are going? We are going from rarer to denser, no? From where to where we are going? We are going from rarer to denser. So for rarer to denser, this is not achievable. Okay. Here I will prove this scenario only. That what will be the value of sine theta c is equals to under root 2 we are getting. So is this possible? Because what is under root 2? Under root 2 is 1.414. So that means not achievable. Not achievable. So I have proved this point. Which point I have proved? That if I am going from rarer to denser, then it will not be achieved. So what was this medium? Rarer medium. This is your denser medium. So when I am going from rarer to denser medium, this cannot be achieved. Say yes or no. Are you agreeing to this point? Rarer to denser, I cannot go. I need to go from denser to rarer. Okay, so these kind of questions can come in one line. That when can you get theta t equals to 90 degrees? So that you will get only when you are going from denser to rarer. So this is the phenomena that I have proved here. Now at critical angle, that means when theta I is equals to theta c, your theta t would become, your transmitted angle will become 90 degree. What I mean to say here is that from where to where I am going? I am going from denser to rarer. Okay, I am going from denser to rarer. This is my incident angle, and then this is my transmitted angle. So this is my incident angle, and this is my transmitted angle. That would become equals to 90 degree. From if you go from denser to rarer. So what is your under root epsilon r1? This is having your relative permittivity of epsilon r1, and this is having relative permittivity of epsilon r2. Okay, so epsilon under root epsilon r1 sine theta c I am writing, because at the angle of theta I is equals to theta c, when theta I is equals to theta c, you are achieving this particular scenario. So under root epsilon r1 sine theta c is equals to under root epsilon r2 sine theta t, and theta t is 90 degree. Is that clear to you? This equation is clear. What we are applying only Snell's law. So I said that when my theta is equals to theta c, at that point my theta t is equals to 90 degree. My transmitted angle is 90 degree. So I just applied the Snell's law. That the relative permittivity of medium 1 is epsilon r1, and relative permittivity of medium 2 is epsilon r2. Okay, and certainly if this is the rarer medium, if this is the denser medium, that means epsilon r1 is more than epsilon r2. This is also is clear, because we are going from denser to rarer medium. So what we are getting? Sine theta c is equals to under root epsilon r2 divided by under root epsilon r1. So from here, your theta c is coming out to be sine inverse under root epsilon r2 divided by under root epsilon r1. So either you can remember this formula, either you can mug up this formula, or you can derive it in the examination as well. It will take one step only. So better than mugging up this formula, in one step you can derive it there as well. That if they ask you the value of critical angle, then this is how you can derive it. Okay. Now, if theta I is greater than theta c, then what will happen? If your theta I is greater than theta c, this I have already told. If theta I, if this angle is greater than theta c, then what will happen is that this will try to come into this medium, and if it is coming back to this medium, that means it will be reflected back with the same angle. So this angle will be the same. Both angles will be same. Let's just say this was some alpha angle, so this will also be alpha angle. So this phenomena is known as total internal reflection. That means we are saying that there is no transmitted wave. Whatever the wave that came, the total wave is reflected back. So this phenomena is known as total internal reflection. Okay, total internal reflection. Again, we are going to discuss this phenomena in a very good detail in the next lecture, and very interesting point I am going to tell about this phenomena, total internal reflection. With the wave analogy, we will discuss it. What do you mean by wave analogy? With the concept of oblique incidence, we are going to discuss this concept again. This is something that we have already studied in 12th class. In your higher secondary classes, you have studied all these things. We are repeating the same thing only, but in the next lecture, we are going to see very interesting thing about these concept, total internal reflection, and I will relate it with oblique incidence. I will relate it with standing wave pattern. I will relate it with traveling wave. So you will feel very good, and then we will study about polarization in this concept. So this is a very detailed concept, very deep concept. Till now, questions has not been asked on this concept, but I am highly sure that in future they will ask a very good question on total internal reflection. Till now, they are asking this question only, these kind of questions that we already studied in 12th class. But if they relate it with the wave phenomena, then it would be very good question. Okay, so we will discuss that in next lecture. But as of now, we are discussing only elementary classes things. Okay, let's solve a question. This is a good question. So this is a medium 0, which is an air. This medium 0 is air. Okay, this is another medium 1 is there, which is having epsilon r value of 2, and this is medium 2, which is having epsilon r value of 1.5. Medium 0, medium 1, and medium 2. This is air, so that means epsilon r naught is 1 here. So from medium 1, a wave is coming, and it is entering into medium. Sorry, from medium 0, a wave is coming, and it is entering into medium 1. From medium 0, a wave is coming, and it is entering into medium 1. So this is the angle theta I, right? The angle is always measured from the normal. So where is the boundary between the surface? This is another medium, and this is another medium. So this is the boundary between two surfaces. Are you getting this point? Which is the boundary between two surfaces? This is the boundary between two surfaces. Boundary between two medium, you can say, or boundary between two surfaces also you can say. So this is your medium 1, and this is your medium 0. So a wave came, and it is making an angle theta I with normal. This is the normal, right? Previously, what was the scene? This was medium 2, and this was medium 1. So this was the boundary, and we connected a normal, and this was making an angle of theta I. Now I inverted it. I just inverted it with 90 degree. So here, this is the separation between two medium. This is medium 1, and this is medium 2. And the wave is striking like this, making an angle of theta I with the perpendicular. This is the perpendicular we are having. From this particular surface, this is the perpendicular we are having. So this is your perpendicular. This is your perpendicular. And it is making an angle of theta I with the perpendicular. Theta I with the perpendicular. So what will be your theta t? This will be your theta t. No. Your theta t will also be measured with the perpendicular. So this will be your theta t. Say yes or no. This will be my theta t. So I am calling this angle as theta 1 actually. Okay. This theta 1 is theta t only. Now what will happen? This wave will go, and again there is a separation between two media. This is your medium 1, this is your medium 1, and this is your medium 2. So again there is a boundary. Again there is a boundary. And what is perpendicular to that boundary? What I mean to say is that, let's make the diagram again. So what happened is that from here the wave was striking at theta I angle, and now it is reflected back like this. Now it is going from rarer to denser medium. It is going from rarer to denser medium. That means it will move towards the normal. So it will move towards the normal. So this is how it has moved. This is how it has moved. Now this wave is striking at this boundary. Now this boundary is also between two different media. This is medium 1 and this is medium 2. Now what will happen? Again it will be, what will happen is that again there will be some transmission. How you will define transmission? With the perpendicular to the boundary. So this is the perpendicular to the boundary. So this angle I am calling as theta 1. So now this wave is making theta 2 angle with the boundary. Sorry, theta 2 angle with the normal. So this wave is making, this transmitted wave is making theta 2 angle with the normal. From here, what you will have? From here you will have some another transmitted wave. Now you are going from denser to rarer. Now you are going from denser to rarer. That means it will move away from the normal. So denser to rarer if you are going, that means it is moving away from the normal. So here there are two kind of transmission. If you are able to see it, there are two kind of transmission. First one is this from air to medium 1, from medium 0 to medium 1. In between there is a boundary. In between there is a boundary. I made a perpendicular. This is my theta I. So there will be some transmitted angle. This is the transmitted angle. Transmitted angle. After that, what happened was this wave was also striking at some other media. At some other media boundary. This is your medium 1. This is your medium 2. So it is again striking here. How much angle it is making? Theta 2. So again there will be reflection and transmission. So we are only caring about transmitted wave. If we are only caring about transmitted wave, so how much angle it will make? Theta 3 angle it will make with the normal. So this is your transmitted wave again. This is also transmitted wave. This is also a transmitted wave. For this boundary, this is working as incident wave. So what is your theta 2? Theta 2 is the incident angle. Theta 2 is the incident angle. Incident angle for what? Incident angle for this boundary. And here theta I is the incident angle for this boundary. This is also the incident angle. This is also the incident angle. So here there are two kind of transmission. And what is this? This is your transmitted angle. I hope you are able to understand the diagram. Say yes or no. Okay. Now find the value of theta I for which total internal reflection is taking place at point B. What I am asking, find the value of theta I. Find the value of theta I for which total internal reflection is taking at point B. That means what do you want? You want your theta 3 to be 90 degree. If you see the first question, what do I want? I want total internal reflection at point B. Find the maximum value. Here I am writing maximum. Okay. In the question it should be find the maximum value of theta. And why it is maximum, that also we will talk about. Why I have written this word maximum, that also we will talk about. But as of now, what do you want? You want this theta 2 to be, you want this theta 3 to be 90 degree. Say yes or no. I want this theta 3 to be 90 degree. So what is my requirement? That my theta 3 should be 90 degree. Can I apply the Snell's law here? Can I apply the Snell's law here? So if I say Snell's law at point B, Snell's law at second boundary, or you can say at point B. So what that would be? That would be under root 2 sine theta 2, under root 2 sine theta 2 is equals to under root 1.5 sine theta 3, which is 90 degree. Say yes or no. So what is the value of theta 2? Theta 2 is sine inverse under root 1.5 divided by 2. So that is under root 3 by 4. So under root 3 by 2. So theta 2 is 60 degree. So what is your theta 2? Theta 2 is coming out to be 60 degree. Well and good. Now we need to find theta I. But if I find theta 2, can you let me know what is the value of theta 1 plus theta 2? Can you see this triangle? Which triangle I am talking about? Can you see this triangle? Yes. Theta 1 plus theta 2 plus 90 degree is equals to 180 degree. So what is theta 1 plus theta 2? That is 90 degree, because this angle is already 90 degree. So theta 1 plus theta 2 is 90 degree. So what I can see here is that theta 1 plus theta 2 is equals to 90 degree. That means my theta 1 is equals to 30 degree. So I already know the value of theta 1. So can I find the value of theta I? Can I find the value of theta I? Certainly I can find the value of theta I. So what I am applying here? Snell's law at first boundary. So what that would be? What is the value of epsilon r1 here? 1 only. So under root 1 sine theta I that I need to find is equals to here theta 1 I already know, and what is the value of epsilon? Under root 2. Under root 2 sine 30. So what I am getting? Theta I is equals to, this is under root 2 and this is 1 by 2. So sine theta I is equals to, this is under root 2 and this is 1 by 2. So this is 1 by under root 2. So sine theta I is equals to 45 degree. So what is the answer of the first one? 45 degree. Now the point is, what I mean to say is that if I send the wave at 45 degree angle from the normal, then what will happen? This will be 30 degree, this will be 60 degree, and this is the critical angle for this particular scenario. This is the critical angle for this particular scenario, you can say, or for this particular boundary. So 60 degree is the critical angle. If your theta t is greater than 60 degree, if my theta t is greater than 60 degree, will you be okay? Yes. If my theta t is greater than 60 degree, then there will be total internal reflection. Do you agree to this point? What is the value of theta 2 we find? Theta t I am saying, theta 2 I should say. So what is the value of theta 2 I find? 60 degree. So at 60 degree, you are just achieving the condition. If I increase more than 60 degree, if I increase my theta 2 value more than 60 degree, this was your denser medium and this was your rarer medium. What we were seeing here, this was your 45 degree and at that you were achieving 90 degree in the previous cases. If I increase it more than 45 degree, then what will happen? Total internal reflection will take place. If I increase more than 45 degree, then total internal reflection will take place. Right? This is what we write here. The value of theta I at which theta r is theta r, again theta r I am writing, theta t, at which theta t is, here I should have written the minimum value of theta I at which theta t is 90 degree. So here as well, when theta 2 is 60 degree, if you increase the angle, then you will achieve total internal reflection. So this is the worst case that we want, that at least I want theta 2 to be 60 degree. At least I want theta 2 to be 60 degree. Now theta 2 is depending on theta 1 value. Because if my theta 1 increases, then theta 2 will go down. Because one thing I know is that my theta 1 plus theta 2 is fixed. Theta 1 plus theta 2 is equals to 90 degree, that is fixed. So if my theta 1 increases, then theta 2 will go down. Right? And if theta 2 goes down, that means you are moving away from the total internal reflection. What you need? You need theta 2 increase. You need theta 2 value to increase. But if theta 1 is increasing, then theta 2 is going down. And if theta 2 is going down, that means we don't want to achieve this condition. Now when theta 1 will increase? If theta I increases. Because if theta I increases, then what will happen? Theta 1 will also increase. This we have already seen, right? In the first one only. If this theta I increases, then this theta t certainly increases. Here also I told you the same thing. If this increases, then this will certainly increase. This doesn't depend rarer, denser or denser to rarer. No. The simple thing is, if your wave is going like this, if this is my boundary, if your wave is going like this, and now you increase the angle, then your transmitted wave will also increase the angle. If this angle is increasing, then this angle will certainly increase. Whether it is rarer to denser or it is denser to rarer. If your incident angle is increasing, then certainly your transmitted angle will also increase. So what I mean to say is that here in this particular scenario, that if I increase theta I, if theta I increases, then what will happen? Theta 1 will also increase. Theta 1 will also increase. And if theta 1 increases, that means theta 2 will go down. And theta 2 will go down. That means you are moving away from total internal reflection. So isn't it the worst case of theta? Isn't it the worst case of theta I? That means maximum I can keep theta I to be 45 degree. Let's just say if I increase theta I to be 50 degree, then what will happen? My theta 1 will also increase. Let's just say it goes to 40 degree. Now if theta 1 is going to 40 degree, that means where will be my theta 2? That will be at 50 degree. And at 50 degree, I cannot achieve my total internal reflection. Because for total internal reflection, this is the minimum requirement. The minimum value of theta t that you require for total internal reflection is 60 degree. So the point here is, if I increase theta I, then theta 1 will increase and theta 2 will decrease. And if theta 2 is decreasing, then I am moving away from total internal reflection, but I need to go towards the total internal reflection. So this is the maximum limit of theta I. But let's just say if I had kept theta I to be 30 degree. If I had kept theta I to be 30 degree. That means I am decreasing the value of theta I. If I am decreasing the value of theta I, that means what will happen? Theta 1 will also decrease. So if theta I is 30 degree, then let's just say theta 1 becomes 20 degree. So what will be theta 2? 70 degree. So at 70 degree also there will be total internal reflection. Why is that so? Because 60 degree is the minimum requirement. If your angle is 70 degree, then certainly there will be total internal reflection. So the point here is a very important point. You cannot increase theta I beyond a certain limit. Are you getting this point or not? So the maximum value of theta I at which you are achieving total internal reflection at medium 2. So that maximum value of theta is known as acceptance angle. Okay, what that value is known as acceptance angle. So I'm writing this point. So this point I'm writing, if we increase theta I beyond a certain limit, then theta 2 value will keep on decreasing and we will not achieve total internal reflection at point B. So there has to be a certain maximum value of theta I for which we are able to achieve total internal reflection at point B. This maximum value of theta I is known as acceptance angle, and we call it theta A. Here your theta A is equals to 45 degree. In this case, what was your theta A? That was 45 degree. Here theta A was 45 degree. Okay, so if my theta I is ranging from 0 to 45 degree, this is also the condition. If it is ranging 0, we cannot take, because then sine 0 will be 0, then this is not our requirement. So if theta I is between 0 to 45 degree, then total internal reflection at point B is achievable. Okay, so theta I here is maximum value is 45 degree. So this is a very important point which will be used when we study our fiber, optical fiber. But as of now, we did not start optical fiber. We are just solving simple problems, nothing else, right? If theta is equal to 60 degree, will there be total internal reflection? Second question, option B. If theta I is equal to 60 degree, no total internal reflection. C. Find the range of theta I for total internal reflection. So the range of theta I is from 0 to 45 degree. This is the answer of C. So in one question only, we understood a very good point, that if I keep on increasing the value of theta I, then theta 1 will also increase, then theta 2 will go down. If theta 2 is going down, that means we are moving away from the critical angle. We need to go towards the critical angle, or we need to have more angle than the critical angle. If we are having more angle than the critical angle, then certainly we will achieve total internal reflection. That's it. Say yes or no. Okay. Let's solve more problems. Let's see this question. This was asked in gate examination only. So I will tell you the scenario. The statement was written here, but as of now, I will tell you the scenario. What is the scenario? This is a very easy question. So this is some medium one. Medium one is water. It is having epsilon r value of 1.75. In the water at distance d, there is a point source which is releasing some light rays. So this is the light ray. This is a light ray. It is releasing. Now, when this angle is equal to theta c, when it is making, and this is your medium 2, which is air. Basically, there is a यहाँ समुद्र है. Okay, there is a sea. There is a sea. Inside there is a point source. So it is releasing some. It is releasing some light rays. This is releasing some light rays, right? In this manner. Now, if it is releasing like this, then what is the angle it is making with the perpendicular? This much angle. So there will be some transmission. Here also there will be some transmission. But now at this angle, at theta c angle, what happened was your transmitted angle was 90 degree. So when it was achieving like this, your transmitted angle was 90 degree. You need to find the distance d. When the wave went like this, then your transmitted angle, this angle became 90 degree. So you need to find the distance d. Can you find distance d? Certainly I can find distance d. First let's try finding the value of theta c. So what will be my theta c? From where to where you are going? Denser to rarer. That means certainly I can achieve total internal reflection. Certainly I can get my theta t to be equals to 90 degree. So under root 1.75 sine theta I, and theta I is equals to theta c only, under root epsilon r1, under root epsilon r1 sine theta c is equals to under root epsilon r2. What is epsilon r of air? That is 1 only. So under root epsilon r2 sine theta t. What is theta t? 90 degree. So what you are getting? Theta c is equals to sine inverse 1 by under root 1.75. What is my theta c? 1.75 under root, then take reciprocal, and then sine inverse 49.10 degree. 49.10 degree. What I need to find? Look, this radius, this is making a circle. From the light rays, it is making a circle, right? This is how it is making a circle. From the light rays, it is making a circle. So this circle has a radius of 5 meter. This is 5 meter. If this angle is theta c, then what is this angle? This angle is also theta c, right? You can see two parallel lines are being cut by this line. If this is theta c, then this is also theta c. Or you can say that if this is theta c, this is 90 minus theta c, and both angle combined is 90 degrees. So this will be theta c only. So this is my theta c. So from here, what I can see is that my tan theta c is equals to 5 by d. Do I know the value of theta c? Yes. So d would be equals to 5 by tan theta c, which is 49.10 degree. What is the value of d you are getting? That's it. So tan you take, then take the reciprocal and multiply by 5. 4.33. 4.33 meter. Okay. It was a very easy question. It was recently asked, as far as I remember. It was recently asked in gate examination. Recently means it was asked in 2000s only. It was not asked in 90s. It was asked in 2000 only. Very easy question. From the point source, light rays are coming, and they are making certain angle. At a theta c angle, you are achieving 90 degree reflected angle. This is making a circle. This is having a radius of 5 meter, and the point source is below distance d in the water source. So that is distance d. So you need to find the value of d. So first I found out the theta c, that is here. So by geometry I solved that theta c is equals to 5 by d. From there I got the value of d, and theta c I was getting 49.10 degree. Very easy, very straightforward. Again, I did not connect the mic, and the sound would have been terrible, right? But now I am connecting the mic. When I discovered that mic is not connected, I record all the video and then I discover mic is not connected. But yeah, I hope you are comfortable with the sound because fan is not on. If fan is not on, then I don't think sound would be that much disturbing. But if fan was on, then it would have been an issue for you. But yeah, that's it. Now we are going to start studying about optical fiber. Till now we were just building up the base. Now we have built up the base. Optical fiber will be able to complete within 15 minutes only. Okay, if you have that good enough base, now you will be able to complete it within 15 minutes only. So I will take a pause, you can also take a break, and then we will come back and start studying about optical fiber. So this is nothing but a waveguide, and it is used to travel the light. So the the word wave I was using, now the wave word will be replaced by light wave. So light is also a wave only. Okay, so it is used to travel the light from one point to another point. Okay, so we will discuss about it. First I will tell you about the structure, and then I will tell you about that it is based on total internal reflection only, and we will build up some formula, and based on that we will solve the problem. Okay, so yeah, let's take a pause and then I will come back. So let's start the optical fiber now. So optical fiber is a kind of waveguide only. It is a kind of cylindrical waveguide, or you can say it is a kind of circular waveguide, and it will transmit the light from one end to another. So here there are, you can see three kind of cylinders there. Plastic jacket is there, cladding is there, and core is there. This is known as core. This is core material, this is cladding, and this is plastic jacket. So this is our this is of no use for us, because this is just for protection. This is just for protecting the optical fiber. So we will study about only core and cladding. Now what will happen is that the light will enter into the core, and due to total internal reflection, it will propagate through this core medium, and it will be traveling inside it. Like inside as well there is a core. Like core is not this part. Core is spread till complete. Like this core will go inside completely. This core is there inside completely. And same goes for this cladding as well. This cladding is also here as well, and it is inside as well. Okay, and same goes for this plastic jacket as well. This plastic jacket is also spread completely. Since we want to show it completely, that's why we are showing it one layer, second layer, and third layer. These three layers are starting at the same point and ending at the same point. Okay, so from here light will enter, and it will travel, and it will be propagated towards the end. It will travel like this. It will keep on traveling like this. It will travel like this, and it will be propagated till the end. Now how the light will travel, that we are going to see now. We already have seen it, but just in this particular scenario in optical fiber we are going to see how the light will travel. Okay, so we are not going to study about this plastic jacket. This is just for protecting it, so we are not going to study it. Now I will just make a 2D structure of this optical fiber, where you will see core and cladding. And what points I have written: a waveguide transmits a waveguide that transmits light to carry data and voice message. So this is your optical fiber. So what it does, it transmit the light, whatever the light that is coming here, it will transmit that light, and that light would be carrying some data and messages. And it works on the principle of total internal reflection. So how it works, that we need to check out. So this is your optical fiber only. What is this? This is your core, and this is your cladding. I am making the inside structure. Core is there, and upper portion of the core is cladding. Downward portion of core is cladding. So this is your core. Upper portion is cladding. Downward portion is also cladding. This is also cladding. I am making a 2D structure. Okay. Now from the air, light wave will come. From the air, light will come. Now what is this? This is your boundary 1. If you remember clearly, this is your boundary 1. Why it is boundary 1? Because from this boundary towards this you are having air, and here you are having core. So this is your boundary 1. Now what will happen? Now what will happen? It will make an angle of theta I with the perpendicular. It will make an angle of theta I with the perpendicular. After that, there will be transmission taking place. So from where to where we are going? This is your rarer medium. So from rarer to denser you are going. Here the scene is the highest. What is this n? N. This is your refractive index. What is this n here? N is refractive index. Refractive index. The highest value of refractive index will be there for core. So n1 is the highest, then n2, and then n0. Okay. Who will have the highest refractive index? Core will have the highest refractive index. So now you are going from rarer to denser. That means you will move towards the normal. So you are moving towards the normal. This is how you are moving, right? Now another boundary is there. This is your boundary 2. This is your boundary 2. Another boundary is there. So again you are going from core to cladding. Now core is having more refractive index. That means epsilon R1 is more than, why I am writing under root. So you can say that epsilon R1 is more than epsilon r2 is more than epsilon r naught. So who is, now this is the core, right? Now which medium is denser, which medium is rarer? This is denser medium, this is rarer medium, right? Because this is having more refractive index. So this is your denser medium, this is the rarer medium. Now you are going from rarer to denser medium. Sorry, I am saying opposite, really sorry. Now you are going from denser to rarer medium. From where to where you are going? Denser to rarer. And if we go from denser to rarer, then we can achieve total internal reflection. Say yes or no. So what I can achieve is that I can achieve total internal reflection. So this was my theta I, this was my theta 1, and can I call this as theta 2? So what will be this angle? Can you let me know? This will also be theta 2, because total internal reflection is there, and for incident angle and reflection angle is always same. So I need to set up the value of n1 and n2, or I need to set up the value of theta I in the manner that I achieve this total internal reflection. So can you set up the value of theta I in a manner that you achieve total internal reflection? Certainly you can set it up. How you will set it up? The question we have seen, no? So in that manner you can set it up, right? So what I need to achieve? I need to achieve total internal reflection. Now I have achieved total internal reflection here. Now here what you will see, again core cladding boundary is there. So this is also boundary 2. Same boundary it is, core cladding. Here also the same phenomena is happening. You are again going from medium 1 to, you are again going from denser medium to rarer medium, because cladding is the rarer medium. So again you are going from denser to rarer. So if I am again going from denser to rarer, what will happen? Again I am having some incident angle here. So what is the value of this incident angle? Can anyone tell me? If this is theta 2, this is also theta 2. What this angle will be? 90 degree. What will be this angle? Theta 1. Why is that so? Because theta 1 plus theta 2 is 90 degree. Theta 1 plus theta 2 is 90 degree. And here this is theta 2, this is already 90 degree. If I call this angle as alpha, so what I get to know? Alpha plus theta 2 is 90 degree. So what will be this angle? This angle will be theta 1 only. Are you getting this point? So this angle will be theta 1. And you let me know one thing, if this angle is theta 1, then what will be this angle? Theta 2. Why is that so? Because theta 1 plus theta 2 is 90 degree. Or you can see, forget about all this geometry, or you can see these are the two parallel lines, which is cut by this line. So if this is theta 2, then this will also be theta 2, right? Or you can see by any geometry. This was theta 1, this was theta 2, this was theta 2, so this has to be theta 1, this has to be 90 minus theta 1, and 90 minus theta 1 is equal to theta 2 only. So this angle is theta 2. So again your wave is incident at theta 2 angle only. So here my wave was incident at theta 2 angle. Again your wave is incident at theta 2 angle. And same scenario is there. From same core you are going to same cladding. Here also you are going from core to cladding. Here also you are going from core to cladding. And same material is there. Same incident angle is there. So if here you achieve total internal reflection, that means certainly here also you will achieve total internal reflection. Say yes or no. Are you getting this point or not? At point B, I had the same scenario, ditto same scenario, that I am going from core to cladding, having incident angle of theta 2. If I am at point C, if I talk about, at point C as well, I am having the same scenario. I am going from core to cladding, having incident angle of theta 2. So here if I achieved total internal reflection, then certainly here also I will achieve total internal reflection. Now can you find out this angle? What will be this angle? Again two parallel lines are being cut with this line. So if this is theta 2, this will also be theta 2. Or you can solve by geometry as well, that this is theta 1. And if I extend this line, sorry, this is not theta 1, this is theta 2. So this is theta 2, this will be 90 degree, this has to be theta 1, this has to be theta 2. So in that manner also you can achieve. Again same scenario is there. You are going from core to cladding with incident angle of theta 2. So if at point B you achieved total internal reflection, then certainly at point D as well you will achieve total internal reflection. So again and again you are getting the same scenario. You are going from core to cladding with an incident angle of theta 2. And at that theta 2 angle, if you are achieving total internal reflection, then again at point C, you are going from core to cladding with an incident angle of theta 2. Again, you are achieving total internal reflection. Again at point D, the same scenario is there. So in that manner, your wave will keep on propagating. So it will keep on propagating and eventually it will get out of your complete optical fiber. So this is how it works. Is that clear to you? All good? Okay. So this scenario we have already seen. Just here we studied how the wave or how the light wave travels. Fine. Now what should be the value of theta 2? What should be the minimum value of theta 2 for achieving total internal reflection? For achieving ACHIEVI, achieving total internal reflection at point B, C, D and so on, minimum value of theta 2, what that would be? That at least this much theta I require, at least this much theta 2 I require, so that I achieve my total internal reflection. What that would be? That would be n1 sin theta 2. I am calling this as sin theta c2. This I am calling as sin, the minimum value of theta 2, that minimum value of theta 2 I am calling as sin theta c2. Okay, critical angle for angle 2. So sin theta c2 I am calling is equals to n2 at the boundary, like at the total internal reflection, like at that angle when you are having theta 2 angle as a critical angle, at that point what will be your reflected wave angle or your transmitted wave angle? What will be your transmitted wave angle? That will be 90 degree, right? I am just finding the boundary, I am finding the minimum value. What I am finding? I am finding the minimum value. Minimum value of theta 2, what you require to achieve total internal reflection. So that minimum value I am finding out. What is that minimum value is coming out to be? From here I can see that theta c2 is coming out to be sin inverse n2 by n1. Okay, so this I can keep in mind, or you don't need to keep in mind, you can just simply do this analysis. Total internal reflection we have seen a lot of time, and at critical angle your reflected or your transmitted angle becomes 90 degree. At critical angle your transmitted angle becomes 90 degree. So this phenomena I used here, that n1 sin theta 2 is equals to n2 sin theta t, but my sin theta t would become 90 degree at critical angle. That is the minimum value of theta 2 that you require for achieving total internal reflection. So theta c2 is sin inverse n2 by n1. Okay, so this is one of the thing. Now there is another thing. What is that? That is acceptance angle. If you remember, is there is something called acceptance angle. Here we studied about acceptance angle. So if you can keep on increasing the value of theta I, then there is some problem for you, because if you keep on increasing the value of theta I, here let's understand. So what will happen is that if you keep on increasing the value of theta I, then what will happen? Theta 1 will increase. If theta 1 increases, that means theta 2 goes down. And if theta 2 is going down, that means we are moving away from total internal reflection. So what will happen at that point? If theta 2 is very less, then what will happen? Some wave will go into this cladding. And if some wave is going into the cladding, that wave will be lost. That power will be lost. Are you getting this point? If we keep on increasing the value of theta I, then what will happen is that theta 1 will be increasing, and if theta 1 is increasing, that means theta 2 will be decreasing, and if theta 2 is decreasing, that means we will not be able to achieve total internal reflection. That means there will be some transmission, and because of that transmission power will be lost. So you will not be able to achieve this transmission inside the optical fiber. So for achieving the optical fiber, you need to have a maximum value of theta I. After that, you cannot increase theta I, because if you keep on increasing theta I, that is a problem for us. So the maximum value of theta I that you can put is known as acceptance angle, right? So what is acceptance angle? What is acceptance angle? So maximum value of theta I at which there is light propagation, there is a possible light propagation forget about it, I will remove that. There is light propagation in optical fiber. Okay, light propagation is possible. I wanted to write the maximum value of theta I at which there is possible light propagation. There is possible light propagation in the optical fiber. So let's find out the value of acceptance angle. Okay, so this I am calling as point A. This I am calling as point A. And one thing I already know. What do I already know? That theta 1 plus theta 2 is equals to 90 degree. This I already know. Now at point A, if I apply Snell's law at point A, what will be the Snell's law? n naught is 1 only because this is air. N naught is 1 only. So 1 sin theta I is equals to n1 sin theta 1, n1 sin theta 1, and at point B, n1 sin theta 2, right? n1 sin theta 2. Now this is the condition. What I am finding? I am finding the worst case. So at theta c2 you are having worst case that you will achieve total internal reflection. So here I am gonna put sin theta c2. Why I am putting sin theta c2? Why I am putting sin theta c2? Because this is the worst case. This is the worst case where you will achieve total internal reflection, right? So this is the maximum value of theta I am finding. So that's why I am putting theta a here. Are you getting this point? Instead of theta I am putting theta a. So at theta I equals to theta a, your theta 2 will become theta c2. Say yes or no? Because if maximum value you have written, that means that is the minimum value of theta 2 required to achieve total internal reflection, and that minimum value is known as critical angle. So theta 2 will become theta c2 here. Is that okay for you? And then n2, and to achieve total internal reflection, that means the transmitted angle should be 90 degree. Is that okay for you? So from here what I can see is that sin theta a is equals to n1 sin theta 1 plus theta c2. What is theta 1 plus theta c2? That is 90 degree. So let's remove this theta 1, so that theta 1 can be removed as 90 minus theta c2. 90 minus theta c2, right? Because what is theta c2? That is 90 what is theta 1? Theta 1 is 90 degree minus theta c2. Okay, so this is equation 1, this is equation 2, and this we are doing from equation 1, and 1, this is cos theta c2 sin theta a. Okay, so from here, from equation 2, what I can find, that sin theta c2 is equals to n2 by n1, So from here what will be your cos theta c2? That would be under root 1 minus n2 square by n1 square. Say yes or no, right? This would be under root 1 minus n2 square by n1 square, right? So from here if I see, so sin theta a will be equals to n1. What is the value of cos theta c2? Under root 1 minus n2 square by n1 square. So what I am getting here, sin theta a is coming out to be under root n1 square minus n2 square. This proof is not tough. This is very easy actually. Where did we start from? We just need to apply Snell's law. If we apply Snell's law, then it is all easy for us. Sin theta a is equals to n1 sin theta 1. This was the at point A. At point B, n1 sin theta c2 is equals to n2 sin theta t. The transmitted angle is 90 degree. From there we got these two equations. Sin theta c2 we are getting n2 by n1. Now in equation 1 if I see sin theta is equals to n1 sin theta 1. So theta 1 I can replace with 90 degree minus theta c2. Right, because both are making, if both are added up, then both added up combined makes 90 degree angle. So from there you get sin theta a is equals to n1 cos theta c2. So from equation 2 you can get the value of cos theta c2, that is under root 1 minus n2 square by n1 square, right? So from here you are getting sin theta a is equals to under root n1 square minus n2 square. And this is known as numerical aperture. What this is known as? Numerical aperture. Okay, this sin theta a value, sin theta a combined, this we call it numerical aperture. So this is the term numerical aperture. So this sin theta a is known as numerical aperture. So sometimes in your question numerical aperture can be mentioned. So you will understand that they are talking about sine theta A, and that is equals to under root n1 square minus n2 square. And what is your acceptance angle? So acceptance angle, you can write down that it is sine inverse numerical aperture. Okay, and what is numerical aperture? Numerical aperture is under root n1 square minus n2 square. So when I say numerical aperture, what should come into your mind? Under root n1 square minus n2 square, and that is equals to sine theta A. And you will never get confused that, sir, whether I should write n2 first or n1 first. You will never get confused here. Why is that so? Because n2 is lesser than n1, no? n1 is greater. So greater value you have to write down first. Are you getting this point? Greater value only you have to write down first, no? So you will never get confused here. So this is your acceptance angle. There are two formula of acceptance angle. So mostly we keep this in mind. This can also be used. Now there is a term called relative refractive index difference that is shown by delta. So this is equals to n1 square minus n2 square divided by 2n1 square. That's it. This is what? This is relative refractive index difference. So this is the formula of it. Okay. And if you solve it more, what do you see here? That n1 square minus n2 square could be equals to 2n1 square delta. If I take under root on both of the side, what I am getting? Under root n1 square minus n2 square is equals to n1 under root 2 delta. Say yes or no? Now what this is equals to? This is your numerical aperture. Your numerical aperture is n1 under root 2 delta. There you go. So there is another relation between numerical aperture, core. What is n1? n1 is the refractive index of core and relative refractive index difference. So this is another relation. So let's write down the summary. What all things you need to remember. So first is the critical angle. What is critical angle? Sine inverse n2 by n1. The second is acceptance angle and numerical aperture. So what is numerical aperture? Under root n1 square minus n2 square. And what is the acceptance angle? Sine inverse under root n1 square minus n2 square. Then there is something called relative refractive index difference. What is that? n1 square minus n2 square divided by 2n1 square. And then there is a relation. What is the relation? That numerical aperture is equals to n1 under root 2 delta. Even if you are not able to remember this, from here within seconds you can derive it. But if you remember it, then also it is good. There you go. Only if you remember these things, your 100% questions from optical fiber will be solved. Only if you remember this slide, that's it. So when you revise, you don't have to revise anything of it. Just go and come to this slide and all revision will be done. And then let's just solve the problem. So what is given? Refractive index of core is given. Only formula based question is there. N1 is given. Now relative refractive index is given in percentage. This is in percentage. So what will be the value of delta? That would be 0.84 divided by 100. What you need to find? You need to find acceptance angle. So acceptance angle can be written as sine inverse numerical aperture. Or what formula would have come into your mind? That's our sine inverse under root n1 square minus n2 square. You are having the value of n1, but you don't have the value of n2. So how will you get the value of n2? Better, what will be the better way? I find the value of numerical aperture. If I find the value of numerical aperture, that would be good for me. Why is that so? Because how I can find numerical aperture? For numerical aperture, I have a formula. That is n1 under root 2 delta. Very easily I can find from here. This formula I am applying. n1. So numerical aperture is equals to n1 under root 2 delta. So what is my n1? 1.62 under root 2 into delta. What is delta? 0.84% is given divided by 100. So this I will get, as far as I remember, that is 0.21. So numerical aperture I will get 0.21. So from here what will be my theta A? That would be sine inverse 0.21. So acceptance angle I will get sine inverse 0.21. 12.12 degree. Very easy, just formula based. See the question, put the formula, that's it. So this we have got, what we have got? We have got the value of theta A. Now what we need to talk about? We need to talk about refractive index of cladding. So what we have got? That sine theta A is equals to, or numerical aperture is equals to 0.21. Numerical aperture is equals to 0.21. And what is numerical aperture equals to? N1 square minus N2 square is equals to 0.21. Do you know the value of N1? Yes. That is 1.62 square minus N2 square is equals to 0.21. So can you find the value of N2 from here? Yes. That would be equals to 1.62 square minus 0.21 square. 0.21 square 0.21 square minus 1.62 square plus minus sign, then take under root 1.606. So N2 is coming out to be 1.606. There you go. This is your N2. So like there is nothing in these kind of questions. Absolutely nothing. If this kind of question is coming in your examination, these are free numbers. Right? So here we have used relative refractive index difference as well. We have used numerical aperture as well. We have used the value of N1 as well. We find the value of N2 as well. Everything we have found out. And from this only they will frame the question. Okay. Now let's talk about power loss. What did I tell you? That it is a waveguide. What did I tell you? That optical fiber is a waveguide. And did we study the power loss in waveguide? In the last lecture only, did we study in miscellaneous concept? Did we study about the power loss in waveguide? Certainly we studied it, right? And what will be the power loss in waveguide? Where Pz is the power at a certain distance z is equals to the inserted power e to the power minus 2 alpha z, where alpha is in Nepper per meter. A very important formula. I hope you know what is your Pz, what is your P naught. I hope you know all these things. What is Pz? Pz is power at a distance z in optical fiber, or you can say waveguide. What is P naught? P naught is the power inserted to the waveguide, or power delivered to the waveguide also you can say. A better word would be delivered. What is inserted? Power delivered to the waveguide. What is alpha? You already know, attenuation constant. And z is the distance, you know. But mark this thing, this formula is applicable if alpha is in Nepper per meter. Now, if in the examination alpha is given in dB per meter, then as a student what I would have done, I know that 1 Nepper is equals to 8.686 dB per meter. This is what I know. So in the examination, if alpha is given in dB per meter, what I would have done, I would have converted it to Nepper per meter and then I would have applied this formula. But there is another concept. You can directly write down the Pz value if alpha is given in dB per meter. What that would be? Pz would be equals to P naught as it is. E will be replaced by 10 to the power minus alpha z by 10. So basically e to the power minus 2 is replaced by 10 to the power minus 1 by 10. This is not equal. I am not saying that both values will be equal. Just this is how I can replace it. Now this formula is applicable. This formula is applicable if your alpha is in here. This formula is applicable if my alpha is in dB per meter. Okay. So in some textbook you will find this formula. In some textbook you will find this formula. Like in 99% of the textbook you will find this formula only. Whatever the textbook that I have read, there was written this formula only. But someone will think that, sir, in waveguide you taught this formula. So why this formula is not applicable? This is also applicable, but this was applicable for alpha is equals to Nepper per meter. And now this will be applicable if your alpha is in dB per meter. Now I will solve one problem using both of the formulas. Okay, using both of the formulas, I will solve the problem. So whatever that you like in the examination, that you can do. So this is the question, and I guess these kind of questions can come from your optical fiber. This is what I am expecting. The next question, if they frame from optical fiber, I guess they will frame the question on power. Well and good. So light pulse propagate through a fiber cable with an attenuation of 0.25 dB per kilometer. Meter or kilometer, that doesn't matter, right? If it is kilometer, then answer will be in kilometer. So don't worry about kilometer, meter, centimeter. This is just a unit of distance. Here the difference is Nepper and dB. And this you need to remember, 1 Nepr per meter is 8.686 dB per meter, right? So what is given? Alpha is given, that is 0.25 dB per kilometer. But we are going to solve using Nepr per meter. So what do I remember? That 1 Nepr per meter is equals to 8.686 dB per meter. Or per kilometer also you can do. Like if I add kilo here, here also I can add kilo. So there is no issue. Basically the thing is 1 Nepr is equals to 1.686 dB. This is the scene. Now here if you divide by meter or kilometer, that doesn't matter. Say yes or no. So what I'm going to do is that from here, what will be 1 dB per kilometer? 1 dB per kilometer will be equals to 1.868 dB, sorry, Nepr per meter. What I am doing is that this 8.686 is coming here. So 1 dB per kilometer is equals to 1 upon 8.686 Nepr per kilometer, right? And what we are finding out, 0.25 dB per kilometer is equals to 0.25 upon 8.686 Nepr per kilometer. So this 0.25 dB per kilometer can be replaced with 0.25 8.686 Nepr per kilometer. So what we are getting, 0.25 divided by 8.686. So 0.0287 Nepr per kilometer. This is what we are getting, the value of alpha. So this was the value of alpha that was given in dB per kilometer, and this we have find in Nepr per kilometer. This is the method 1 we are solving. We will solve by this method as well. Now what I can apply, determine the distance z through which the power of a pulse is reduced by 40%. So which formula we are going to apply now? Pz is equals to P naught e to the power minus 2 alpha z, and this will be applicable if alpha is in Nepr per meter. So now power is reduced by 40%. That means it has become 60% of the maximum power. Reduced by 40%. Reduced by 40% means it has become 60% of the maximum power. So at z equals to z1, Pz1 has become 60% of the maximum power, right? Reduced by 40% means 60% of the maximum power. So now what I am gonna write, that 0.6 P naught started with P naught e to the power minus 2 alpha z1. My target is to find z1 now. So my z1 will be ln 0.6 minus upon 2 alpha 1, and alpha 1 value I already know, that is 0.0287. 0.0287 into 2 reciprocal into 6 ln. So you are getting 8.87 kilometer. So Z1 value is 8.87 kilometer. So this is the answer you are getting. Okay, and this answer is absolutely correct. Let's solve by method 2. So in method 2, alpha is given as 0.25 dB per kilometer. I am not going to change anything. What I am going to apply, Pz is equals to P naught 10 to the power minus alpha z by 10. This is not that easy to remember. What I usually remember is that P naught e to the power minus 2 alpha z. This is what I remember. Then P naught e to the power minus 2 is replaced by 10 to the power 1 by 10. E to the power minus 2 is replaced by, E is replaced by 10, then minus alpha z, forget about this 2, then divided by 10. This is how I can remember this formula. If you directly go on remembering this formula, it would be a bit tougher. Like as of now, you feel like that, sir, okay, I can remember it, but in the examination hall, you can forget it. So usually we remember this formula, this one. Usually remember with this one, because that is very easy, because E naught e to the power minus alpha z we already remember. So this is very easy to remember this one, but this may become tough sometimes. Okay, so what we need to find, at 0.6 P naught 10 to the power minus alpha z1 by 10. Okay, so what you are getting, z1 would be equals to log 10 0.6 and then minus sign is there, divided by alpha into 10. Say yes or no. And what is the value of alpha? That is 0.25. So what is the value of Z1 you are getting here? 0.6 log into 10 divided by 0.25 and then plus minus, that is 8.87 kilometer. This is your Z1. The same answer you are getting. So one formula you need to apply, you can think on your own which formula you need to apply. I guess this is something that is easier to remember, but here there is a lot of calculation, because in optical fiber they will mention in dB per kilometer only. Okay, if the question is coming from optical fiber, because optical fiber can propagate the power till longer distance. You can see the distance is 8.87 kilometer. So you have worked for 8.87 kilometer and this has reduced only 40%. Power is reduced only 40%. You have worked for 8.87 kilometer. But in waveguide we see the parameters was in centimeters. So in waveguide mostly they will give this value in Napier per meter. But in optical fiber they will give this value mostly in dB per kilometer. So that's why in the textbook you find this formula. You find this one. But both formulas are equally important. Both formula you can apply, but it's up to you that how to remember both of the formulas. I told you the trick. E to the power minus 2 will be gone and it will be replaced by 10 to the power minus 1 by 10. This is how you can replace it. Let's solve one more problem. A 10 kilometer fiber is there with an attenuation of 0.2 dB per kilometer, serves as an optical link between two cities. How much power is received? So you need to find the received power. How much power is received of the maximum power? Basically, the question is incomplete, I guess. How much of input power is received? Yeah, this is written. How much of input power is received? How much of input power is received? So our input power was P naught. When he worked the distance of 10 kilometer, it will be reduced. So how it will be reduced? 10 to the power minus alpha z by 10, where alpha is in dB per kilometer. So that much power will be taken, right? And at what distance we need to find? At 10 kilometer. So z is equals to 10 kilometer. So at 10 kilometer, what is the seam? So what will be the power at 10 kilometer? That would be P naught e to the power minus alpha. Now alpha will be in dB per kilometer, that is given 0.2 dB per kilometer into 10 kilometer divided by 10. So P naught, alpha is 0.2, z is 10 kilometer divided by 10. It is not E, really sorry. It is 10 to the power something. So what you are getting? 10 to the power 0.2. 0.2 plus minus 10 to the power. So 0.63. 0.63. This is what you are getting. So P at 10 kilometer divided by P naught is equals to 0.6309. That means 63.09% power is received. From here, if 100 watt power was going, initial power was 100 watt, then only 63% of the initial power has been received. Are you getting this point? Okay. So 63% of the total power or initial power has been received. 63%, or you can say 63.1%. Is this the answer? Yes. 63.09%. These questions are from Sadiku only. Okay. Since it is mentioned in Sadiku, that's why we are solving it. So whatever that is mentioned in Sadiku, like mostly if you see gate PYQs, no. So all the concept, mostly all the concepts are coming from Sadiku only. The concept from antenna is coming from Balanis, and some concept from transmission line is coming from Cheng. So these three are the books which you need to refer as an educator, as a student also. If you want to refer, then you can refer, but whatever that is required for you, at least 90% of the things we have covered from there. And also we are following Shiv Gankar sir's playlist as well. So from Shiv Gankar sir's playlist as well, we are covering everything. From NPTEL as well, we are covering everything, and from these books as well, whatever that is required, we are covering everything. So in the end of the last lecture, I will tell you what all things we have covered, from which playlist, from which textbook, from which part, what all things we have covered, so that you would be confident that at least this much part of textbook I know. But in the end of the next lecture, I will tell you, because next lecture will be the end of our EMFT, right? So yeah, now the thing is, like 99% chances are there that if they want to frame a question from fiber optics, then they will frame till this point only. But there is another concept, very small concept is there, that is known as V number. V number for an optical fiber. So we need to study about that V number as well. What did I tell you? Optical fiber is a waveguide. And in waveguide, what do we study? That how many modes it can propagate. So same goes for fiber optics as well. Because what is optical fiber? Optical fiber is a waveguide. So in this waveguide, how many modes will propagate? So that thing we are going to see now. And that thing is defined by V number, and it is known as mode volume, or you can call it normalized frequency. So the V number is given by, there is a formula that you want to remember, that you have to remember, that is pi d upon lambda into numerical aperture. This is the V number. So they can ask you what is the V number for a particular optical fiber. So there pi you already know, lambda will be the wavelength of the light that is being propagated. So lambda will be the wavelength of the light that is being propagated. D is the diameter of core. Okay, what is D? D is the diameter of core, and numerical aperture you already know. Now from using the V number, we will find number of modes being propagated. What did I tell you in our rectangular waveguide? What did we find? That how many modes will be propagated. How we used to find it? First we used to find the cutoff frequency. Then for having, if my f is greater than all the cutoff frequency of, let's just say T10 mode, T11 mode, T21 mode. So all these modes will be propagated. This is how we used to find it. First we used to find the cutoff frequency. First we used to find the cutoff frequency for different mode. And if our operating frequency is more than that cutoff frequency, then we would say that T10, T11, T21, TM21, TM22, all these modes are being propagated. This is how we used to find it. Here, what we have found? We have found V number. Now using the V number, you can find the number of modes being propagated. So how many modes will be propagated, that we need to find. So that number I am calling as N. Now there are different kind of optical fiber. In the examination, how to you need to solve the problem? In the problem, if step index fiber is written, step, if the word step is written, then you need to apply the formula V square by 2. First you will find the V number. V number is same for everyone. This formula will be applicable for all kind of optical fiber. Pi d upon lambda numerical aperture. But if the step word is written, you need to apply V square by 2 formula. If parabolic word is written, there will be written that it is graded index fiber with parabolic refractive index profile. So if parabolic word is written, you need to apply the formula V square by 4. And if a triangular word is written, you need to apply the formula V square by 6. Is it tough for you to remember? No. Look, I am not telling the meaning of triangular profile. I am not telling the meaning of parabolic refractive index profile. I am not telling the meaning of graded index fiber. I am neither going to tell you the meaning of step index fiber, because this is 1% important for your examination. Only 1%. So better than spending the time on concept, we will spend the time on problem solving. That how to solve the problem. So what they will ask you? They will ask you the number of guided mode propagating in fiber. For that, what you need to do? You need to apply the formula. Number of modes they are asking. Okay, that is equals to either V square by 2 or V square by 4 or V square by 6. So how you need to start? Okay, step is there, V square by 2. Parabolic is there, V square by 4. Triangular is there, V square by 6. What is V? Pi d upon lambda into numerical aperture. What is D there? D is the diameter of core. That's it. This is the complete summary. Is that okay for you? Okay. Now this formula n equals to V square by 2, n equals to V square by 6 and n equals to V square by 4. That is only applicable if your V number is significantly higher than this particular value. You will see that your V number will be coming very, very high. It would be coming 500, it would be coming 600. So if it is very high, then only it will be applicable. This formula is applicable only if your V number is significantly higher than this particular value. This particular value you don't need to mug up. I am just saying that your V number should be pretty higher. And in the examination, if the question is coming, then 100% sure is that the V number will be higher than this one, because they want you to apply this formula. So this is just a point I wanted to deliver, that this formula is applicable. N equals to V square by 2, V square by 4 and V square by 6 only if your V number is significantly higher than this particular number. Let's solve the question now. What is written? Step. Core diameter is given 80 micrometer. Wave is propagating at a wavelength of 0.8 micrometer. Numerical aperture 0.21. Find the number of modes find the number of mode fiber can propagate. So number of mode we need to find for step index. Then you need to repeat the same question for graded index fiber having parabolic refractive index profile. So what word I see? Parabolic. And repeat the same question for triangular refractive index profile. So you need to repeat this question for step, parabolic and triangular. Now V number is same for everyone. This V number is same for everyone. That is pi d upon lambda only. Pi d upon lambda into numerical aperture. So what is pi? Pi is pi. What is d? Core diameter is given. Divided by lambda 0.8 micro into 0.21. So what is that V number? 21 into pi. So 65.973. This is the V number you are getting. So your V is 65.973. So this is common for everyone, right? This V number is common for everyone because the formula of V is common for everyone. Now for first one is for step. For step index. What is the formula? N is equals to V square by 2. So what you are getting? V square by 2. So they are saying that number of modes being propagated is 2176.24. But this is not possible. This has to be integer, no? 1 mode will be propagated, 2 mode will be propagated, 3 mode will be propagated, and 10, 15. So it has to be integer. So what will be the value of n? N value will be 2176. So this much modes are being propagated. Step for parabolic. For parabolic, what is the formula? The formula is V square by 4. N is equals to V square by 4. Okay. For that we are getting the answer 1088.12. But certainly this is not applicable. What will be applicable? 1088. This is for parabolic. And for triangular, the n number is V square by 6. So what you are getting? 725.41. 725.41. So what is the value of n you are getting? 725. So for triangular refractive index profile in graded index fiber, your number of modes being propagated is 725, then it is 1088, and here it is 2176. Very rare chance that these can be asked, but certainly in ECE these kind of questions are very famous. In ECE, that finding number of modes. Okay, now there is a very small point, one last point I wanna tell, that if V number increases, then number of propagating modes will increase. If you increase the V number, the number of propagating modes will also increase, right? Now, if you want single mode operation, if I want single mode operation, then what do you think? What should be the value of V? What I want? Single mode operation. That means I want my n value to be 1. But even if I get n value to be 1.9999999, what I will take? N value to be 1 only I will take. Say yes or no? Here the n value I got 2176.24. So what will be the n value I will be taking? Only the integer part, no? So n value 1 I will take. So now I need single mode operation. That means I need only one mode. That means I need the value of n to be 1. So what all value of n I can have? Till 1.99999. Say yes or no? So what I mean to say is that if I want single mode operation for step index fiber, so what I'm gonna put? That n value I can have till 1.99999, V square by 2. So from here I will find the value of V. So what value of V you will get? Nearly equals to 2. So you will say that if V is nearly equals to 2, that means maximum value of V you can have. Maximum value of V you can have for single mode of operation is 2. But the catch here is that this formula is not applicable for V equals to 2. This formula is applicable when your value of V is, where it is gone? When the value of V is significantly higher than 2.405 under root 3. So practically it is found out that the maximum value of V practically it is find out that the maximum value of EV at which single mode will be propagated, that value of V is 2.405 for step index fiber, and it is 2.405 under root 2 for parabolic and 2.405 under root 3 for triangular. Are you getting this point? The maximum value of V at which you will get only single mode of operation. What you need single mode operation. So maximum value of V at which you will get single mode operation. For step index it is 2.405. For parabolic profile it is 2.405 under root 2, and for triangular profile it is 2.405 under root 3. Is that clear to you? So it is practically find out. If I apply the formula, my V value is coming out to be 2, but actually it is 2.405. Now a lot of students have this doubt that, sir, why it is 2.405? So it is practically found out. You cannot apply this formula n equals to V square by 2 for values lesser than 2.405 under root 3. So here my V value was coming out to be 2, which is lesser than 2.405 under root 3. So I cannot apply this formula. So as per this formula, I cannot find it out. So practically I have found out that for single mode of operation, what I have found out for single mode of operation, so the maximum value of V number such that the fiber, what is written here, such that the fiber supports only single mode operation, that is known as normalized cutoff frequency, okay, which is shown by Vc. So the value of Vc is, for step index it is 2.405, for parabolic index it is 2.405 under root 2, and for graded index it is 2.405 under root 3. Again I am saying for gate aspirants this is very rare that they will ask any question from here, but will you be able to remember the terms that if step is there, then n equals to V square by 2. If parabolic is there, n equals to V square by 4. If triangular is there, n equals to V square by 6. What is the maximum value of V for which you will support only one mode of operation? That is 2.405. If you increase the value of V above 2.405, let's just say my V value I am getting 2.5. That means certainly one mode will not be supported. It can be 2 mode, it can be 3 mode, that I don't know. But if you want only one mode to be supported, that means your V value should be maximum 2.405. Say yes or no. Okay. So for step index it is 2.405, for parabolic profile it is 2.405 under root 2, and for triangular profile it is 2.405 under root 3. Let's see a question based on it. So graded index fiber with parabolic. Refractive index has a refractive index of core. N1 is equals to 1.5. And relative index difference of 1%. Dial value is given as 1%, which can be written as 1 by 100. Find maximum possible core diameter that allows single mode operation at a wavelength 1.3 micrometer. What do you need? Single mode operation. What you need to find? Maximum possible diameter. This is what I need to find. So what is my, for single mode operation? For single mode operation, what is the maximum V I can have? The maximum V I can have is Vc, and that is equals to 2.405 under root 2. 2.405 under root 2 for parabolic profile, right? So my Vc is V max, you can say, and that is equals to Vc, that is 2.405 under root 2. And what that would be equals to? What is your V max? Pi d upon lambda. So here d max you will take. Pi upon lambda d into numerical aperture was there. So which maximum you can take? Maximum of d only you can take, no? So d max they are asking is equals to 2.405 under root 2, right? Pi value we already know. What is lambda? 1.3 micrometer. 1.3 micrometer. D max I need to find. What is my numerical aperture? So my numerical aperture is equals to n1 under root 2 delta. This formula I have already studied. So what is your N1? My N1 is 1.5. 1.5 into under root 2 divided by 100 is equals to 2.405 under root 2. So what is D max? So 10 to 24.05 divided by 1.5 into 1.3 divided by pi. 6.63 micrometer. There you go. That is your complete optical fiber. Okay, nothing more will be asked from this particular topic. Again I am saying, after this there is very rare chance for questions to be framed, but you can revise it very quickly. V number pi d upon lambda into numerical aperture. We need to see the words step, parabolic and triangular. For step, v square by 2, parabolic v square by 4 and triangular v square by 6. Then we can solve this problem, and we need to remember that this is applicable for significantly higher values. Then what we studied, there is a cutoff value, that this is the maximum value of v you can have, so that only single mode propagation is applicable. So for step it is 2.405, for parabolic it is 2.405 under root 2, and for triangular it is 2.405 under root 3. Then we solved this question where they asked us to find the single mode propagation. Propagation is single mode, so what is the VC value I can have? 2.405 under root 2. So using that value, I find out the value of D max, that is 6.63 micrometer. There you go. That's it about your complete optical fiber. Thank you very much. Next video will be the last video of our complete EMFT, and I guess I have covered every single thing that can be asked in upcoming future examination, at least till 2030. Okay, at least till 2030 I have covered everything, because after 2030 the pattern may change. If I am alive, certainly I will bring more content for sure. Okay, so again and again, like if I see some good question, then I will add it up in the playlist. If I see some good concept that I did not teach, if I learn from somewhere else, then also I will add it up. So things will keep on adding up. Now in the next video we are going to learn that concept which you will find nowhere. Only in NPTEL you will find. Like no one teaches that concept in GATE industry. But what I feel is that the question can be framed from that particular concept, and that will be, we will study total internal reflection only, but in a good manner. Here we said that if there is total internal reflection, that means there is no transmitted wave. But actually there is transmitted wave, and that transmitted wave will be decaying wave with propagating in a certain direction. And because of the reflected wave, we will have a standing wave pattern. Along with that, we will have a traveling wave as well. So all these things we are going to prove it, and then we will see another concept related to wave polarization. Okay. Thank you very much. Let's meet in the next video.